Right. So I have finished the simulation, and that by that I mean Simulink has completed compiling and solving the simulation. Well, with regards to the solver that's being used, I have kept it at auto. The same can be set for the step size as well. On keeping it variable step and the solver to auto, I'll have let simulation determine what's best based on its observation of the model. I have kept 0.2 seconds uh, simulation time from our last model. It was brought in since we saved it from what we obtained in lecture 5. So let's view the results, and it's extremely close. I'd say within 95% to what we have obtained based on the studies and activities I have carried out in lectures 3 to 5. So I don't think there's any worry with regards to our model being error free. So now that we have a perfect model up and running, what we can do is one of the foremost things that we can do is we can change the DC motor parameters based on the datasheets of other motors, other permanent magnet brushed DC motors, and check out uh, a change in performance results. So we could find a better motor for the application based on what we described as better. If we want the motor to gain a vertical position in lesser amount of time, then perhaps we'd have to have a motor with a higher torque rating or a higher stall torque and apply the characteristics to this scope and run it and see whether our objective can be achieved. And if we don't need it to be achieved within 0.2, we can opt for a cheaper motor and see what the performance might be. So based on what you define for the requirements, we can vary the motor parameters and check whether your requirements are met. So that's one of the tasks that you can carry out with. It's kind of a motor sizing task. Right. Let's will quite sum up our activity of modeling a rod attached to a PMBDC motor and predicting the results based on the voltage that we apply. So our next step would be to replace the motor type with a stepper motor and power it using different pulse patterns and see what the performance might be. If it were not for the Simscape, if you was developing the motor side and the inertia side using Simscape blocks, then we would have had to compile another set of equations to model the torque of the stepper motor and implement them using Simulink blocks and change the connections between those blocks and implement the final effects through an ideal torque sensor. So that would have been quite a tedious task. But since we have now dealt with the motor side using a combination of relatively simple blocks with the hard tasks hidden within a black box, what we can do is we can just remove these blocks, bring in the Simscape blocks for the stepper motor, connect the controllers as we would in a physical world, and provide the PWM signal as we would in a physical world, and run the simulation, carry out, and see what the performance is. So that's the advantage of sticking with Simscape blocks, and we'll see that in our next video.